Can we hear fish talk? Isn't that such a wonderful thought? Just to be clear, we are not talking about hearing sounds underwater, but rather, can we hear sounds when we are above the ground?
Okay, so maybe fish can't really talk, which is hard to believe after watching Finding Nemo. But the real question we're trying to answer here is about sound and whether sound can propagate between mediums. In this case, that's the air and water interface. Hi, I'm Nikhilesh.
And I'm Kushal,
And we're the two broke scientists. Okay, so from high school physics, we know that sound is a vibration that propagates as a pressure wave. And we know a couple of things about sound. First, sound needs a medium to travel through. And we also know that the properties of the medium dictate the speed of sound in that medium. Think of it like this. If you had a tube and you started vibrating one end, the particles near the end of the tube get compressed and then rarefied. And that is what propagates as a disturbance through the pipe. That is the picture of sound we learnt in high school.
But what if you had a new medium at the end of the pipe? What would happen to the sound waves? But before we get into that, let's revisit some high school physics. Suppose you had two billiard balls of the same mass, while one is stationary and the other is moving towards it at a given velocity. If you consider a perfectly elastic collision, based on the laws of physics, which is nothing but the conservation of momentum and kinetic energy, we can say that after the collision, the moving ball comes to a standstill, whereas the stationary ball now moves with a velocity that is equal to the former. Now, if the mass of the stationary ball starts increasing, you'll observe that the behavior changes. The heavier the secondary ball gets, the more it impedes the energy transfer from the first ball. So much so that if the weight of the secondary ball is much higher than the first one bounces back with the same velocity it initially had.
So there is a formula to quantify how much energy is transferred between balls which undergo elastic collisions. Now, for sound waves, something very similar exists. So suppose you had a packet of particles that are carrying sound energy through a medium, and those packet of particles now impact on an interface, and on the other side of the interface you have particles which are more dense. The initial set of particles will not be able to transmit their full energy to the other medium, and some of that energy is reflected back, similar to the balls. So the property of a medium by which it creates this pushback is called acoustic impedance.
So how do we quantify impedance? For a plane wave traveling through a fluid, the acoustic impedance is given by ρ times V, where ρ is the density of the fluid and V is the speed of sound in the medium. The unit for impedance is kg per meter square second, which is also called as rel. The acoustic impedance of air is about 3500 times less than that of water. There is a formula that calculates the intensity of sound that is reflected and transmitted between the mediums based on their density. Do you notice something about the formulas? Isn't it exactly the same as the one for the colliding balls?
Isn't it amazing how physics manifests itself the same across different fields? Now, if you take the formula we just showed you and apply it to the air and water interface, you see that more than 99% of the energy of the sound wave is reflected back. Now keep in mind that it doesn't matter which side of the interface you approach it from, whether it's from the air or the water, the formula remains the same. Basically, if there is a huge mismatch in the acoustic impedances of two media, then most of the energy is reflected back. And there is very low transmission of energy across the interface.
Now coming back to the most important question, can we hear fish talk? Well, human hearing is extremely complex and a sensitive phenomenon. Our ears can pick up pressure perturbations of just about 20 micropascals against an ambient pressure of 1 lakh pascals. So, our ears are indeed extremely sensitive. So, even though the air-water interface attenuates sounds by quite a lot, 30 decibels to be precise, we can still hear faint sounds. For the exact numbers and calculations, do check out the links given in the description below. So technically yes, we can indeed hear fish talk if everything is perfect and ideal. But for all intents and purposes, the air-water interface is known to be an almost perfect mirror for the propagation of sound waves.
Acoustic impedance has applications in many fields, including the medical field. If you've ever been to the ultrasound of a pregnant woman, you see that the doctor first applies a gel on her belly before using the machine. Basically, this is because there is a large acoustic impedance mismatch between air and the skin cell tissue, and the gel has properties in between both those medium. So, by applying the gel, the doctor is able to ensure that most of the ultrasound is able to pass through both the media and not get reflected back.
Thanks for watching. We hope you enjoyed the video. If you do have any comments or suggestions, do leave them in the comment section below. As always, don't forget to like, share and subscribe. Bye!
Alright guys, so you might have noticed a bit of change of scenery around me. Well, it didn't snow in Delft. It rarely does. What happened is, I started my PhD at the University of Waterloo in Canada. So I moved here about a month ago, while Kushal started his PhD and he's continuing at Delft. So even though we'll still keep uploading videos, we won't be in the same place anymore. Also, I want to give a huge shout out to Yash Abang for helping me film this video. Thanks Yash.